Hello and welcome to Engineer's Mindset. So in this video, we are going to be looking at planar density of FCC 111 plane. Okay, planar density can simply be defined as a ratio of the number of atoms that makes up a plane to the area of the plane. So mathematically, you have that planar density P dot D is equal to the number of atoms that make up a plane divided by the area of the plane. Okay, divided by the area of the plane. Now, for FCC structure, let's start first by drawing our simple cubic structure. So from our simple cubic structure, you have this. All right, so let's consider here to be our y-axis, consider here to be our x-axis, consider here to be our z-axis. So we are given the plane, okay, we are given the plane 1, 1, 1, okay, so this simply means that h is equal to 1, k is equal to 1, and L is equal to 1. That is the Miller indices. Now we find the intercept. Now for the x-intercept, it is always taken as 1 all over h. And this is equal to 1 all over h is equal to 1. So you have 1 all over 1. This implies that this plane cuts x at 1 because 1 divided by 1 remains 1. For the y-intercept, it is taken simply as 1 all over k, and this is equal to 1 all over, again, k is equal to 1. So you have 1 all over 1, which simply implies that this plane also cuts y at 1. Okay, and for z, you have it to be 1 all over L, and this is equal to 1 all over L is also given there as 1, so 1 all over 1, which implies that the plane cuts the z plane at what? 1. So which means our intercept plane x, y, and z is going to be what? Also 1, 1, and 1. Now for the simple cubic structure, all the parts are 1 meters apart. So that means from the origin to this point remains 1. From the origin to y also remains 1. From the origin to z also remains 1. Now we need to draw the plane 1, 1, 1. So it means that a cut x at 1, okay, and a cut y at 1, and a cut z at 1. So from the origin, x1, you have here to be 1. You mark it out. From the origin, it cuts y at 1. This is 1. Also mark it out. From the origin, it cuts z at 1. This is also 1. You mark it out. Now you join all the points together. So join from y to z, join from z to x, join from y to x, and you have this. Now this seems or looks like an equilateral triangle. Let's pull out the triangle over here. So you have your equilateral triangle. Okay, then again, don't forget that at each corners we have corner atoms. We have corner atoms at each corners. We have corner atoms for a simple cubic structure. At each corners we have corner atoms. At each corners we have corner atoms. Okay, let's keep this side since we don't need this. All right. Okay, at each corners we have corner atoms. Okay, so I've neglected putting the corner atoms at all the side. Let's take off this as well because we won't be needing this. Okay, now so let's impute the corner atoms here. So we have corner atoms here, we have corner atoms here, we have corner atoms here. Okay, what makes this then a face center cubic structure is simply because from the name face center cubic, at each of the faces we have central atoms. Okay, so that means if I consider this face, if I consider this face here, if you consider this face here, okay, we have a central atom. We have an atom centered there. Directly opposite to this face, directly opposite to this face is this other face. Okay, directly opposite that face is this other face. We also have a central atom. So we have a central atom. So the two of them combine to provide one full atom. So be very careful now to observe that this central atom has not cut this plane. This central atom has not cut this plane, just like this central atom is cutting this plane. Be very careful to observe that. Similarly, considering the upper plane now, considering the upper plane, we have central atom. Also be careful to see that this central atom has not cut this plane either, but directly opposite the upper plane, we have the lower plane. So this plane beneath, we also have a central atom. This central atom and this central atom combine to provide one full atom. Now, considering this outward face here, considering this outward face, we also have a central atom. Okay, now directly opposite this outward face is the face behind, or the inward face. Directly opposite that face, we also have another central atom. So the two of them combine to provide one full atom. So you observe that for this phase, we have that this atom is cutting this plane. Again, for this other phase, this central atom is cutting this plane, and for the lower phase, this central atom is cutting this plane. So which means for the phase center cubic structure, we have central atoms, we have central atoms, we have central atoms. Okay, so that is what the structure looks like. Now we need to find the area of this plane from the formula number of atoms divided by area of the planes. So let's start first by calculating the area of the plane. How do you calculate the area of the plane? Remember earlier we said in all our videos that this is a corner atom, this is a corner atom, and the separation between two corner atoms, distance from one corner atom to the other, we call that the lattice constant, which is symbolized by A. Similarly, distance between this corner atom to this corner atom is also called the lattice constant, symbolized by A. Now you observe that this triangular arm, or this equilateral triangular arm, is making a right angle triangle with this. So call here point A, call here point B, call here point C. So this arm A to C, which is the arm of the equilateral triangle, is forming a right angle triangle with A, B, and C. So let's pull out the right angle triangle. We can do that over here. So considering that right angle triangle, you have something like this. So this is A, C, and this is B. We have corner atoms, we have corner atoms, we have corner atoms. Not forgetting, from A to B, distance between two separate corner atoms, we call that the lattice constant, A. So from A to B, this is A. Also, from B to C is also what? A. So from B to C is A. Now we are looking for AC, which is the arm of the equilateral triangle. Okay, so how do we find AC? Simply by employing our Pythagoras theorem. And from Pythagoras theorem, AC all squared is going to be equal to AB squared. And AB is equal to A. So that means AB squared becomes A squared plus, again, we have BC squared. And BC is equal to A. So BC squared becomes A squared. Okay, so AC all squared is now equal to A squared plus A squared. This gives us 2A squared. So this simply means that we can make AC subject of the formula by taking the square root of 2A squared. So this simply implies that AC is equal to, of course, you can find the square root of A squared, that is simply A, then 2 remains in the square root. So AC is simply A root 2. All right, so that means this AC is A root 2. And since this is an equilateral triangle, it means all the arms are the same, A root 2. So distance from here to this point remains A root 2. Also, distance from here to this point also remains a root 2. All right, now same thing as distance from here to this point. Okay, the arms of the equilateral triangle are the same, so it remains a root 2. Okay, so having found the arm, we need to now find what is the area of the plane. Since this is an equilateral triangle, the area of an equilateral triangle is given simply as half base times height. That is the area of an equilateral triangle. So which means we need to find the height. What then is the height? To find the height, that means we have to bisect the equilateral triangle into two. And if you do that, it now means that distance from here to the center of this bisection becomes what? If this is a root 2, then that means bisecting this equilateral triangle into two, this distance becomes a root 2 divided by 2, because we have now splitted this distance into two. Same thing as from here to this point also remains a root 2 divided by 2. So we have now splitted this arm into two to find this height, the height of the equilateral triangle. Okay, so we can take this plane off now. Okay, so that means, okay, so let's put at the right angle triangle that we have now from here to this point. We are looking for h. This distance now is a root 2 all over 2, and this distance is simply a root 2. Now we employ Pythagoras theorem once more. Call here A, B, and C. So from Pythagoras theorem, BC squared, okay, BC all squared is equal to AB squared, AB all squared plus AC squared. So plus AC all squared. Now, what is BC, which is the hypotenuse arm? From B to C is A root 2. So you have A root 2 all squared is equal to, we have AB squared, and AB is actually A root 2 divided by 2. So you have A root 2 all over 2 all squared plus, then we'll have AB, and then we'll have AC, and AC is the height we are looking for, h. So that becomes h all squared. So we need to make h subject of the formula. But before then, a root 2 squared becomes what? Of course, root 2 to the power of 2 becomes 2. So you have 2 times a squared. That gives us 2a squared. And this is equal to, same thing happens here. Root 2 squared becomes 2. Then you have a squared all over. Remember, there is 2 here. So 2 squared becomes 4 plus h squared. Now we make h subject of the formula. H squared is now going to be, this becomes 2a squared minus 2a squared all over 4. So this simply implies h squared is equal to, now let's obtain 2a squared minus 2a squared divided by 4. This is going to give us 6a squared all over 4. Okay, so I can take this off. So from here, 6 goes, so from here, 2 goes into 6 is 3, 2 goes into 4 is 2. So I have h squared is equal to 3a squared all over 2. So we can simply find the value of h to be the square root of 3a squared all over 2. You can also break this down to be h equals root 3a squared all over root 2. So this simply implies that h is equal to, I can find the square root of a squared, that is simply a. So 3 remains inside of what? The square root all over, remember here we have square root of 2. Okay, so this remains the height of that triangle. If this is the height of the triangle, then we can now find the area of the triangle. So we can do that over there. So we said area of that equilateral triangle is half base times height. So this means area equals 1 all over 2 multiplied by the base. Now, the base simply is this distance from here to this point, and distance from here to this point is measured as a root 2 all over 2. So you have multiplied by base, which is a root 2 all over 2, multiplied by the height. I will just obtain the height here as a root 3 all over root 2. So you have multiplied by a root 3 all over root 2. So you observe that root 2 cancels root 2 over here. That means area is equal to, I have here a times a. This gives us a squared. We are left with root 3 as the numerator all over. Then I have 2 times 2, and that gives us 4. That means the area of that triangle is simply what? A squared root 3 all over 4. Now, having found the area, what do? Simply, next thing to do is to find the number of atoms. So, watching the area of the plane, now we need to find the number of atoms that makes up this face center cubic structure 111 plane. Now we find the number of atoms that makes up this equilateral triangle. Usually, we know that atoms are spherical in shape, and therefore the angle of a sphere is simply going to be 360 degrees. But let's consider each of these corners. For this corner, the atoms we are considering are atoms enclosed inside of the triangle. So these shaded regions are only the parts we are considering. These shaded regions are only the parts we are considering. Same thing as these ones here. So we only consider the shaded region because these are the ones enclosed in the equilateral triangle. Now, for an equilateral triangle, the angle that makes up this plane is 60 degrees. For an equilateral triangle, the angle that makes up this plane for an equilateral triangle remains 60 degrees. This angle here remains 60 degrees. But we know that a full atom is supposed to be at this corner, but only 60 degrees of this atom has been taken out of the full atom, the angle of the sphere, which is 360 degrees. That means this particular corner has total number of 60 degrees atom all over 360 degrees. The same thing happens to this corner. This corner atom has only 60 degrees atom out of 360 degrees. This same corner also takes only 60 degrees number of atoms out of 360 degrees number of atoms. Okay, now let's consider the central atom. Now, for the central atom, we have a whole complete sphere which makes an angle of 360 degrees. But this sphere has been bisected into two. We are only considering half of it inside of the triangle, and half of 360 remains 180. So, which means this body is simply taking 180 degrees out of 360 degrees atom. Same thing happens here. This centered atom here is taking 180 degrees out of 360 degrees complete atom. Same thing here. This atom is taking 180 degrees out of 360 degrees complete atom. Now let's find the values. 60 divides 360 simply gives us 1 all over 6. Similarly, 60 over here divides 360 also gives us 1 all over 6 atoms. Also here, 60 divides 360 gives us 1 all over 6 atoms. Again, 180 divided by 360 over here gives us 0.5 number of atoms. Similarly, 180 divides 360 over here also gives us 0.5 number of atoms. Also, 180 divides 360 here gives us 0.5 number of atoms. Now, let's find the number of corner atoms and the number of central atoms. So, number of corner atoms is now going to be equal to, we have 1 all over 6. Okay, let's take this off. We have 1 over 6 plus 1 over 6 plus 1 all over 6. That's the corner atoms. 1 all over 6 plus 1 all over 6 plus 1 all over 6. This is simply number of corner atoms gives us 1 over 6 plus 1 over 6 plus 1 over 6. That gives us 0.5. So the number of corner atoms are simply 0.5. Okay, whereas for the center atom, number of center atom, this is going to be equal to, we have 0.5 plus 0.5 plus 0.5. So you have 0.5 plus 0.5 plus 0.5. So that means the number of central atom becomes what? 1.5 atoms. Therefore, total number of atoms becomes the sum of the central atom and the corner atoms. That becomes 0.5 plus 1.5. So this simply gives us what? 2. So which means for the FCC 111 plane, total number of atoms is equal to 2. Now, when you know the total number of atoms and you know the area of the plane, then you can compute the planar density. Therefore, planar density, okay, PD is equal to number of atoms is 2. You have 2 all over the area of atom here. We have a squared root 3 all over 4. So that gives us a squared root 3 all over 4. So this is going to be equal to 2 all over. Let's find root 3 divided by 4. Let's obtain root 3 divided by 4. That gives us 0.4330 squared. Okay, so let's now find 2 divides 0.4330. This simply implies that planar density is going to be equal to 2 divides that answer. We'll have that to be 4.62 all over a squared. The unit remains atoms per square meter. Okay, so that becomes the planar density of that given structure FCC 111 plane. All right, guys, so that's how you find your planar density for that given structure. In the next video, we are going to be looking at planar density for BCC 111 plane. I hope to see you in that video. Do well to like our videos, comment nicely, share to your friends, and if you're new to the channel, do well to appreciate our work by subscribing and turning on your notification bell to keep getting updates when more videos such as this drops. I will see you in the next video. Thanks.